Thank you, Anya, for the introduction and also the invitation to present here in this forum. So I'm Jeremy Adams. I'm the Vice President of our Renew MAT group at the Western Research Institute. So in our group, we do renewable upcycling, carbon materials, and asphalt technologies. And I'm a chemist. I have a PhD in chemistry, and I've been here at the Institute for more than 11 years, working in a lot of spaces and hydrocarbons, not just asphalt in particular. And then JP, do you want to?
Sure. So I'm Jean-Pascal Planche, JP. Very pleased to be here and see a number of names in this webinar that I've met in the past and interacted a lot in Europe when I was still in Europe. So it's good to be back, kind of. And so I'm now the CEO of Western Research Institute. I joined WRI 13 years ago. And I will let Jeremy explain a little more what we do at WRI, but you will see that this presentation today is really in the heart of our activities. So this is a great opportunity for us to explain what we are doing at WRI. Thank you.
Yogesh?
Yeah, thank you, Jeremy. Yeah, hi, this is Yogesh Kumbargiri. I'm a lead research engineer here at WRI, working in the Renew MAT group, where Jeremy heads, and I'm sure Jeremy will talk a lot about the group and in general things. So my training and everything is in civil engineering. So bachelor's, master's, PhD, everything in civil engineering, and have had experience with respect to on the performance end and the construction and everything, along with my PhD and all that. So now I'm trying to help out here with the group with respect to the performance, rheology, and then chemomechanical. So all these were different things that we are doing. So thank you again. Thank you, Anya, and thank you, Ian, for inviting us. And it's great to speak here at this important meeting. Thank you.
Okay, thank you. So we can go ahead and get started with the presentation. Just want to ensure that you're seeing my slides.
Perfect, thank you.
Okay, wonderful. So I am also going to go ahead and turn off my camera during the presentation part, but then I will turn it back on at the end. So thank you for this opportunity to speak and to kind of give some of our perspectives and a little bit of the activities we have going on surrounding alternative binder solutions for sustainable and greener pavement. So we have obviously a great team here at WRI. I wanted to acknowledge some of those folks. And we have a couple different groups here, one mainly on the chemistry side and one on the engineering scale-up side for processes. And then we have a few folks from the University of Wyoming School of Energy Resources that are helping us develop some of our alternative binders. So particularly Elsie Mueller and Trina Pfeiffer. So this is our facility. We have several buildings, a large campus, more than 22 acres. And our mission is really to partner and innovate, develop, and commercialize technologies using advanced sustainable chemistry, analysis, and innovative engineering for carbon, natural resources, and waste. And our vision is to really be a world-class leader in reimagining tomorrow's energy and materials for a lower carbon intensity and sustainable future. And of course, we want to do this locally, but also, the reality is most of our money actually is international money, and so we participate a lot in the international community on these activities. So we are our own nonprofit company since 1983. We just celebrated 40 years. We're located here in Laramie, Wyoming, and we have a long history with hydrocarbons in general, and developed a lot of advanced technologies. A lot of them have been centered around petroleum and coal products and processing, and we do have pilot plants that can handle several barrels of heavy oil partial upgrading and deasphalting. That's a major activity for our engineering group. We have a lot of programs running on hydrocarbons beyond combustion, and these can be things for asphalt or additives or carbon materials. And we have done quite a bit of work on mesophase pitch and carbon fibers and carbon foams. We have developed quite a versatile toolkit that's unique to WRI. We have a lot of our own patented technologies that we do use internally, but we do license them. And so we have, again, to be able to go from the chemistry all the way up to pilot scale. And then we have some of these methods, such as what's shown at the bottom, the SARA-AD, which is an advanced separation for hydrocarbons, which gives us a good fingerprint of the composition. And then we have begun working more and more in the last several years on circular economy issues. And so this is being done primarily through our waste reengineering initiative, where we do a lot of bio-upcycling of plastics and resins, things like wind turbine blades, and even some aged asphalts and RAS and what we call carbon ore, because a lot of people are uncomfortable with the idea of coal these days. And so this is a little bit more of a neutral term, but we do a lot of work on coal to products. And we also have manage and run a Peterson Asphalt Research Conference every year. This year, we just did our 60th conference, and it's been continuous. We're even able to keep it going through COVID. But this conference is really centered around kind of the binder and a lot of aspects on the binder chemistry and its performance and modification. So at the heart of this push to go to alternative binders is really to help address the issue of climate change and reaching some of these net zero goals. So everybody understands that this curve here is showing that if we continue to do business as usual, we will continue to put in greenhouse gases into the atmosphere. These will continue to raise the temperature of our planet and can lead to some non-desirable effects for the rest of us living here on this planet. So if we want to reduce the temperature, we need to change really how these greenhouse gases are being produced, and if they are produced, how we handle them. And so we really need to change the way that we are making our energy, we're using our energy. And then really to get down in this region where we hit net zero, we're going to have to incorporate a lot of carbon removal technology, so carbon capture, utilization, and storage, because we've already put in, more than a century of CO2 in the atmosphere, and we're going to continue to have processes occurring on Earth that will continue to generate CO2. So we need to remove those, and that is the only way to really reach a net zero, and then eventually maybe in the future to really go to net negative. And so we really need this complete transformation in how we produce, transport, and consume energy. Now, to achieve this, there are a variety of roadmaps on how we might reach net zero. And this is just one example, but all different maps have something in common, and that is a huge cut in all of our fossil fuel related activities. And so a big one being our dependence on crude oil. And so this plot here is showing that, essentially we need to drop down from 90 million barrels per day all the way down to less than 30 by 2050. And there are also many other, if we look at more details in the map, there are other kind of key points that have to deal with how the crude oil is consumed for fuels. And if we just focus on those, we see that in the time that we're at right now, we need to have a situation where we're not doing any new oil and gas fields, no new coal mine extensions, all of these activities. And then by 2030 and 35 and 40, we need to reach various milestones in how the transportation sector is using fossil fuels, and we need to have electrification occurring at a very high level. So by 2030, we'd need about 60% of cars to be electric. By 2035, 50% of heavy trucks. And by 2040, we really need a change in the sustainable aviation fuels by, where at least 50% of all the activities in aviation, are fueled in a different way. And now, of course, there are other technologies being developed and things may change, but this is with some kind of broad brushstrokes, some mechanism and goals and ways that we could achieve and start to get towards net zero. So if we think about electric cars, because it's something that there's been a lot of data generated on, to see if we're actually going in the right direction or not. So CNN last year had published an interesting article, they had this conclusion that internal combustion powered vehicles sales peaked in 2017 and have been in a permanent state of decline since then. And they talk a lot about, what are the reasons behind this? And of course, there's a lot of government incentives, tax breaks, and different things to go ahead and purchase an electric vehicle, get the infrastructure set up in your house to charge it and do these kinds of activities. But they notice that in some countries that don't have these incentives, that there's also a rapid adoption of electric vehicles. And that's because the younger generations really feel a sense of stewardship and being responsible for the environment. And so they see this as a personal thing for them to do as an activity to participate in helping with global warming or climate change in the future. And so if we look at sales, so this is some very recent data, just updated here just like a month or two ago, that in the United States, it took 10 years to reach the first sale of 1 million electric vehicles. And then to get to the second million, it took 2 years. And then they just crunched the numbers and saw, it took us only a year to reach the third million. So they're now able to sell 1 million electric vehicles per year in the US. And so there's, of course, a big ramp up in sales in other countries. And then on the fuel side, looking at more sustainable fuels for combustion engines and also aviation fuels, there's been a huge ramp up of activity in our country. And so this plot is showing, the expansion in renewable diesel capacity. And we can see that, again, this trend is almost exponential as well. And I can tell you personally that we have felt this in Wyoming because we're a very oil and coal and gas rich state. And we do have multiple refineries. 2 of the largest refineries very close to where we are in Laramie, Wyoming, they have completely converted to renewable diesel. And so these were refineries that were producing crude oil, but they were also large asphalt suppliers for the region. And so they're no longer supplying asphalt or bitumen. And so we see that, the petroleum asphalt or bitumen binder, this supply is under threat. So we see there is really a change in how the values. We see there's a change really in the markets. We see that, there's actually supply now, a real meaningful supply of different types of renewable fuels and technologies, electrification, and all of these activities that are occurring. And so how is, in the paving industry, we know some aspects in how we're going to reduce our CO2 emissions, but we need to be realistic about where the bulk of these emissions are coming from. So when we look at emissions, typically there's a scope 1, a scope 2, and a scope 3. And so scope 1 is and 2 are really the ones that, as a company, we can have a lot of control over, because scope 1 is basically, the energy and everything else that's going on at the facility to do our activities. And so these are going to be, the production of making, typically producing the mixture and laying the pavement and doing all of these kinds of activities. And for all the workers. And so this we can have a direct impact on. Scope 2 is, kind of the electricity that's used in the process and to power and do the different activities. And so, a person can switch to renewable fuels. They can switch to renewable energy from wind, for example. So in Wyoming, we are an energy-rich state. We've always been exporting energy, and now we have many, many, many wind turbine farms across the state. And so we're producing massive amounts of renewable wind energy. So a person could make a decision to plug into that and control those emissions. But the reality is that for most companies, about 80 to 90% of the emissions are scope 3. And so these are things that are upstream and downstream from the activities of that particular company. And so it's a little bit lower in the paving industry, because in the paving industry, that's kind of energy intensive for all the heating of the aggregate, the heating of the binder, the transportation, usually long distances, have to use the fuel, the heavy equipment. But the reality is that a big chunk of the emissions is still this scope 3, which is the upstream and downstream. And in particular, the upstream, which is where do we get our feedstocks, our materials, our bitumen, and what's the CO2 associated with that bitumen? And so we can look at two different extremes, and I apologize, these numbers are quite small, so you may not be able to see them. But on one side, we have basically a scenario of a well-managed conventional crude oil. And then on this side, we have kind of an extreme of an extra heavy oil that has to be processed a lot before we can get the fuels out of it at a refinery. And so there's a lot of emissions associated along the way of just production of crude oil and then going through and producing the various products from that crude oil. But if we just focus on the upstream, and again, this is just getting it out of the ground and taking it to a refinery to be processed, that there's a significant amount of CO2 associated with using crude oil. And again, there's a wide range, between a conventional and a heavy. And here in the United States, we have a combination of both because we still are getting a lot of heavy Canadian crude coming through on pipelines, and it has to be upgraded so it can meet the pipeline specification, and there's a lot of emissions associated with that. So also there have been other studies. So there was one done in 2012, and it was presented and published at EUB3721, and they showed, again, we're about in the same range for those CO2 emissions per ton of bitumen. So we know that asphalt or bitumen, that this is a byproduct of the refining process, because the refining process is really there to extract the fuels for transportation, and then of course lubes and petrochemicals and these other types of products. When the Asphalt Institute did a life cycle assessment, they looked into the different details. They said, okay, in the US, we're going to make some average about conventional crude sources, heavy crude sources, and all these different aspects. And they even went in and looked at how does this affect if you add different additives such as SBS, polymer modification, and different things. And again, this was not, I would say, a complete analysis, because they didn't account for the performance in the pavement later on. This was really looking at getting your materials and taking them and applying them to the road as a pavement. So they didn't consider the lifetime savings that could come from certain modifications or using better materials. But it is a good starting point. And what they saw there is that basically 65% of the emissions are due to the fact that we're using crude oil as a basis of getting our asphalt binder or our bitumen binder. And so, how, and again, this comes in that scope 3 emissions. And so, if we can find different sources that don't have so much emissions associated with them, we could really reduce the CO2 footprint. Again, we could do a lot in the other activities of paving, again, switching the energy sources, switching the fuel sources, going to warm mix or cold mix, and cold in place recycling. There's a lot of things that can be done, but we will not erase this initial amount of CO2 emissions because of the material that's being used. So this is really where it comes in, where having an alternative binder can make a big impact on the CO2 emissions for the paving industry. So NAPA, the National Asphalt Pavement Association, they have a variety of goals on how to help decarbonize the asphalt industry in the United States and in North America. And they are really looking at, all kinds of aspects, scope 1, scope 2, and scope 3, but they haven't really weighted and said, what is going to be the biggest impact. And so we've seen already, looking at scope 1, 2, and 3, we understand now through the Asphalt Institute study and everything, where the biggest impact could be in helping to reduce emissions. But when we look at their goals for the upstream scope 3 emissions, I just want to point a couple things out. And they say that, we need to really start looking at research for new forms of asphalt binder, bitumen binder, and the binder replacements. And then also, again, this is also a very important aspect. We also need to continue to look at research where we can increase the wrap content greater than 40%. So again, this is a savings, this is a savings, yes, for part of the binder, but really for the virgin aggregates and everything that's associated with getting those aggregates and fines and all of those and putting them in the pavement. So we know in the last couple years, there's been really this huge shift in the US. It's probably the shift has already been occurring in a large part in Europe, but it really hasn't been discussed and hasn't been made a priority in the US until just this last year. So last year, the General Services Administration, which is making some policies on basically all federal projects, and of course the federal government is the biggest purchaser of asphalt and user, and so they are saying, you know, that we need to now look at not just the materials and the performance, but we need to look at, you know, their global warming potential, and they want to now, you know, when they go to do a job, they're going to have to look at the different material and say, okay, this one has a higher CO2 footprint than this one. If the cost isn't too, you know, isn't preventative, then we need to use the one that's going to have the lowest global warming potential. And this is really going to be determined through that environmental product declaration statement, which again is this like nutrition label of the various environmental impacts. But they're really focusing on the CO2 emissions, and they tie that directly to the global warming potential. So the federal government says we have to do this, and there have been some state Department of Transportations that have also been very proactive, and they have already made their own policies, and they are in place. And Colorado, California, Oregon, and there's many other states that are have this written in, trying to get these type of policies also passed for their states. And the Federal Highway Administration has also issued a whole series of climate change challenge projects. And so this map here is just showing the various states that are competing on those and carrying out those various projects. You can see it's quite significant. There's a lot of states that are participating, really trying to help again decarbonize the petroleum asphalt binder, bitumen binder part of what's being done. Also, of course, recycling and these activities. NAPA has started their Road Forward Consortium, and so this is a consortium of industrial partners that are really focusing on ways that we can help reach net zero and decarbonize the pavement industry. And you can see every month they're signing new MOUs and getting more partners on board, and so this is becoming a very important activity for them. There are lots of companies, you know, that are also looking on their own outside of whatever policies in the different countries are going on, looking for different, you know, alternative binders. And they're really focusing on renewable carbon or waste carbon. And we had a call more than a year ago with one of the largest contractors in the world. And they said, you know, we don't have a choice anymore. Our investors are telling us, you know, that you must do this. And so, you know, their funding and their investments are being tied more and more to some of these decarbonization goals. And a lot of these companies have set up very large sustainability groups to try and address these issues. So is this something that's really coming? And it is. There are companies that are making significant progress. So Shell, Bitumen, they have launched their carbon sink products, and they have got multiple paving trials that are going on, and then Eiffage with their Biofalt product. You know, they've been using that for many years now, proven that it has a very good performance, and so they're starting to sell that product and use it in motorways and different applications. This is not directly related to paving, but it's, you know, other industries that are tied to the petroleum industry to make products and the binder. You know, they're also looking to decarbonize and how to handle their waste. And so for the roofing industry in the U.S., the Asphalt Roofing Manufacturers Association, they also made some new policies last year, and this has to do with kind of more on the Scope 3 emissions on the downstream side. They want to reduce landfill disposal of their asphalt-based roofing products, and so they have various goals, you know, by 2035 and of course by 2050. So if we look at what's in the literature for kind of alternative binders, the point of this map is to say, yeah, it's complicated and there's lots of things out there. Not that you can read anything that's on here, but there, you know, in this particular review paper, it's already a little bit dated. It's from 2020. They looked at 93 papers on alternative binders, and a lot of them were basically academic, and they're looking at different feedstocks, you know, waste cooking oils, different plant and animal oils, things like swine manure. That was very big for a while. It's went away. Natural rubber latex, biochar, cellulose type of feedstocks that are processed in different ways, and also lignin. And so, there's a lot of, things that are all being kind of combined and used and looked at. And, where people are saying, okay, we made a process. I got something that's kind of black and sticky. Let's use that. And, and so we need maybe some focus and some direction on maybe what are the best sources to use, because some of these are not going to be appropriate because the volumes are just not there, and the volume may never be there. Maybe you could develop a local product, but if you're going to do wide scale paving applications throughout a country or through, across countries or different states, we're going to have to be realistic about the limitations on some of these feedstocks. So if we think about biobinders, so these are things that are coming from new biogenic carbon. Of course, it's always appropriate that these be something that's not competitive with food sources. And so if we look at lipid-based things like vegetable oils, cooking oils, it's extremely limited pool. If you look at palm oil, soybean oil, I mean, these are vast, sources, and they could easily supply, for the paving industry a feedstock, but the reality is, a lot of it gets used for food, and then there's a huge ramp up in capacity right now, but this capacity is all being diverted to biodiesel and renewable diesel. So even though there's a lot of it out there, it's really limited in the short term. Now, this may not be true in the future, because we just saw that there's this rapid increase in electric vehicles. And again, heavy trucks are also going electric, and also, sustainable aviation fuels. There's been some talk of electric airplanes, hydrogen fuel cells, and different things. So if some of these technologies really take off and are widely adopted, there could potentially be a huge glut or supply of some of these vegetable oil-based or vegetable oils. The other products that have been developed are from rosin and pitch, primarily from the pine industry. And again, these have been made into successful products, but there's a limitation on availability of these materials. And then a lot of these materials like rosin, they have a lot of high value outlets already. So there's a lot of pull, again, on that feedstock. If we think about solid cellulosic biomass, this is a very large feedstock. Again, this would be something that could be appropriate, but again, this value comes from things like the paper industry, the construction industry, things going into the municipal waste system and different things. And so this feedstock is quite scattered, and then you're going to have to convert it. You're going to have to do some process to get it in an appropriate form, change those molecules so they work well as a binder. And, there may be all kinds of sorting issues, and then source variability. So switchgrass is going to be completely different potentially than pine, than cotton, than, I don't know, different types of woods and all of these aspects. Lignin is another source that may make sense because it's something that gets produced and isolated as a byproduct primarily from the paper industry. There's a significant amount of it, and most of it actually gets burned or landfilled, and only about 2% gets commercially used. Again, there's some issues, of course, because there's source variability based on which kind of cellulose source was used, and then there are different processes for producing paper and extracting the lignin. And again, this material typically is probably something that's going to require some kind of conversion, because typically it's not miscible in the bitumen. And so as a binder replacement, there probably needs to be something done with it. But there's been a few reports showing that you can get some CO2 reduction by replacing 25 to 50% of the binder with lignin. Other things we can look at are secondary carbon waste. And so these can be things from manufacturing waste or municipal waste. So ground tire rubber is one good example. It's something that's been used because whenever we go get new tires, we have to pay a fee, and that fee goes directly to help in the recycling of those tires. And then there's been a lot of technological development to turn that into a product that works well in pavement. And the other thing that is a little bit unique to the aspect that we're bringing is to look at carbon ore. Again, when we say carbon ore, we're really speaking about coal, but coal is a dirty word and no one wants to speak about it. But if we look at this resource dispassionately, we see that there's billions of tons of this material. And if we're not burning it for energy, what is really the main issues with using this as a feedstock for materials. It's going to require conversion again, like a lot of these other feedstocks. And the main hurdle, I think, really with carbon or coal is really this negative public perception about using it for anything. Many people I've talked to through the years says, why would you do anything with coal? Just leave it where it is in the ground. So when we talk about processing our materials, there are different ways to get to something that may be useful for a binder. And so we can do pyrolysis. This is kind of the traditional method that's used. It's high temperatures. You make a lot of gas. Typically, that gas goes as emissions. And also, you tend to produce PAHs. So one of the things is when you apply high temperatures to molecules, sometimes they can rearrange and condense, and you cleave off a lot of different groups that are on any aromatic units, and this can lead to formation of PAHs. And so this is something that we can actually do unintentionally when we're cooking, for example. And again, the products from that are usually hydrophilic, so they're going to have some issues with water. You usually co-produce a ton of water, and that's energy intensive to remove. And a lot of these liquids and byproducts usually are corrosive. And, one of the things in the literature, when we look at the literature and we say, there's all these pyrolysis products, coming from wood, coming from different wastes, coming from whatever. And one of the things that a lot of people don't address up front is the PAH content. And so, realizing that this process is going to be more prone than any other process to make those PAHs, a lot of these studies probably should do this evaluation of pHs first and then decide to continue or stop after that. But many of them are continuing to make their bio oils through pyrolysis or different waste oils and continue to carry them forward without looking at the polycyclic aromatic hydrocarbon content. We can do other methods, and they can be chemical or solvent liquefaction. These have benefits over pyrolysis in that usually you have a lower temperature, you produce a lot less gas, sometimes no gas. You're going to reduce the amount of pHs that you unintentionally kind of co-produce in the process. And then you can tune, a lot of the properties. You can get very hydrophobic materials, which of course is going to be similar to the bitumen. And there's two main ways for this kind of processing. One is hydrothermal, which is where you use water. Of course, it's attractive, but sometimes you can get a lot of polar functional groups, and it can be very polar, and so it may not be really appropriate. And then you can use solvents, and solvents are great because certain reactive solvents, you can tune all kinds of properties in your material. But the issue there is you have to be careful because it could be expensive. And then, you have to consider the life cycle assessment, about, kind of that scope 3 emissions again, about your downstream, how energy intensive and all this is it for the solvent. So alternative binders, we need to make sure that they work in current asphalt production and paving equipment. We're not going to invent a whole new set of equipment to do this. The hydrophobicity is something that's important because if you have something that's hydrophilic, it may work well initially, but once water gets in there, you can get some stripping, debonding from the aggregate, and then there can be leaching. Again, this can be tuned if we use solvents. Adhesion can be an issue because the molecules, again, are a different set of molecules. They may not have the right properties. That can be overcome with various chemistries. There could be cohesion issues. So how those molecules stick to one another, do they, because asphalt, it kind of pulls apart in these strings because the molecules are highly attracted to one another. But in some of these alternative binders, you can actually just break apart because there's this lack of cohesive forces. Of course, this can be overcome by adding polymers. That's why most alternative binders have polymers. There can be issues in solubility or miscibility. So again, if we're going to do recycling with petroleum bitumen, we're going to need to make sure that it's going to have to continue to be recycled. And so whatever we put on the road needs to be highly compatible with that. Again, we can tune that if we use different solvents. We could have significantly different densities, and this could lead to phase separation with things like different additives that are added or polymers. Oxidation may be completely different. We could have all kinds of different products, different severities, and we could add different environmental contaminants potentially. Weathering could be an issue. Again, On the practical side, super pave specifications are used a lot in the US. And so we've actually seen that in some cases, these are not very meaningful because these materials have a completely different physical response with temperature and load. And then we have to be careful too, because if we're using a lot of vegetable oil or different things, we could potentially run into issue where we have some biodegradation. We could get some attack by bacteria or fungus or different things. And then, of course, the main one that goes along is, is this really going to be practical or not? Has to be available. There has to be logistics. We have to have good performance. Has to be able to be recycled. And then, of course, in the very end, something that's going to help with the CO2 emissions. So we just wanted to look quickly at a couple products that are out there. One is from Shell, their carbon sink. They're saying that they are basically it's not a full replacement alternative binder. It's more of an extender. So they're replacing about 20% of the bitumen with a biogenic carbon source, but they're able to reduce the CO2 emissions for their production of bitumen. But then also in the end, when they do paving, they are actually storing some CO2 emissions because of that biogenic carbon into the pavement. Eiffage also has some products out there. There was a big study on the bioreprobation project, and the biofalt was used, and they used it with 40% RAP. Again, that was for economics, but using a high level of RAP also helps with the CO2 offset. This is a material that's made from tree pitch, rosin, some SBS polymer, and then a flux. This was mixed 2 on this particular trial. This is a loaded test section that they followed, and what they saw was that the biofalt product here is mixed 2. It's difficult to see, but it's the very top line. It did have a little bit more rutting than the other materials, but but the rutting was completely acceptable. And then when they looked at the extent of cracking in it, it's actually down here at the very bottom. And so after many thousands of loads, they didn't have any cracking. So this product was a little bit softer, of course, lending itself to a little bit of rutting, but then also less cracking. So one issue with it was they did notice that if you heat it above 150 C, you did get some more VOCs coming off. But the reality is if we want to go to lower application temperatures anyway and use it as a warm mix. And so this actually has an advantage at reducing CO2 emissions. We just need to be aware when it gets used that we use it appropriately and not heat it too high. And so the biofalt's a kind of a combination of 3 factors to reduce the environmental impact. And this is a high amount of the reclaimed asphalt, application at lower temperatures, and then using, again, this plant-based binder. So no bitumen is being used. So really they're, hitting a lot of those kind of scope 2, scope 3 emission type of issues. It's been found to be compatible with all traffic loads. So it's a plant-based binder. So again, it's from the forestry and paper industry. It's a certified bioproduct. It does have very good miscibility and compatibility with the old bitumen and the reclaimed asphalt. And again, it is also, because it's a component has this biogenic carbon, we're storing some of that CO2 now into the pavement. So here are just some examples of some paving sections that were done with this particular product. It's something that we've worked with because we were also on the bioreprobation project, and then we've also done some other evaluation. It appears to be a very good product. On the U.S. side, Iowa State University, they are also working on various ways of using basically soybean oil to produce different products for paving. And so at the heart of their technology is they have a sub-epoxidized soybean oil. So the economics will work out if they do sub-epoxidation versus fully epoxidized soybean oil. But they've created a lot of different products for warm mix and hot mix and different ways of using it, and for different seals, and also some cold in place recycling. They've also developed a reaction of this material to produce a polymer, and this is just showing that their polymer you can use less of it and you get a much higher stiffening effect. So here's basically the base binder. It's a very soft PG 4634. If they blend in 3% SBS, you get that increase in stiffness, a reduction that you would see in rutting. And then using only 2% of their soybean reacted polymer, then they see there's this huge massive effect in increasing the stiffness of that product. So they're looking at all kinds of different products, and one of the ways they're envisioning this, really being a win on the environmental side and also on the cost side, is using these different aspects of using a high amount of wrap and different materials. So traditionally in the U.S., we use kind of a higher grade paving grade base binder, and then we do some polymer modification. And sometimes, with I guess it's debatable, but the SBS could be a specialty grade polymer. And then, that's kind of the status quo. And they say, well, we could really do much better if we use a high amount of wrap, and then we use basically some very off-spec generic vacuum tower bottoms. And then we go ahead and we can formulate with our Biomag subepoxide soybean oil, and then we can pave at a much lower cost. And then again, we're adding biogenic carbon, we're saving on the virgin aggregates and inputs because we're using a high level of wrap. So I want to move over to some of the things that we're doing at the Western Research Institute. So we have multiple projects, and one of the big ones, though, is with the University of Wyoming and School of Energy Resources on the coal refinery. This technology is taking the coal and processing it in multiple different ways and getting multiple products. And again, doing this without consuming coal as a fuel source. So if we want to get from coal to something that's going to act like a binder, we're going to have to do some processes and some chemistry. And of course, when we do that, we're not going to get a full conversion. We're going to have some side products. Typically, there's some more coke-like material, and then there's some inorganic ash. But whenever we run a process, of course, we're going to create some emissions. But in this program, they're very sensitive to trying to create a net zero process. These emissions that come from the process can be taken up by a couple different methods. One, they have an algae program, so they're growing algae with CO2 and creating products from that. And then they also have the methane reformation, where they can make synthesis gas. And again, of course, if we use a lot of renewable energy, which we have a lot of now here in Wyoming, and we do this practice of carbon capture, utilization, and storage, we can have a net zero process. And they're advancing, what to do with the other side products. So there are some rare earth elements in coal. Some of the coke or char type materials, they're converting into a lot of building materials, and they've actually built a house here with the Department of Energy funding. They're making soil amendments that seem to be working well to help retain moisture and add some nutrients to the soil. And they're also doing coatings and other chemicals. So, we had mentioned there are some limitations of using anything that's going to be derived from vegetable oil feedstocks, but in the long term, this may be something that may make sense, especially in paving. So if we think about vegetable oil or vegetable oil-based solvents, we can, if we don't just use vegetable oil, but we combine it with other materials, we can extend, at least in the short term, the availability of that vegetable oil. So if we're not just polymerizing straight vegetable oil, but we're taking the vegetable oil and combining it with a high amount of something else to get us the properties we need, we're going to have more vegetable oil available to use as an asphalt product. And if we use vegetable oil, if you take 1 kilogram and you use it and you turn it into like a paving product, you're going to store about 2.8 kilograms of CO2 per kilogram of vegetable oil that's used. So Mother Nature, of course, is very good at taking CO2 and converting it into other things that we can then use. We developed a process that's low energy. We don't have to put hydrogen or catalyst. We don't make any gas. And we're getting this chemical reaction between the vegetable oil-based components and the coal. And again, so our product now has a high amount of biogenic carbon in it. So it is going to store CO2 in our pavement. So we're looking at making new asphalt materials and recycling agents from coal. And again, we're focusing on coal, but these concepts work for a lot of other feedstocks as well. Coal actually makes sense in some respects compared to a crude oil. And if we look especially at the upstream CO2 emissions, again, that's extraction and taking it to the refinery. This has been well studied by the Department of Energy that Wyoming Powder River Basin coal, which is one of the largest reserves of coal in the country, it has 3 times less CO2 emissions than a conventional crude oil. So that's something that is kind of interesting, and a lot of people would not think that there would be anything favorable in the CO2 story to say about coal. But to use it as a feedstock for materials, it's actually probably one of the lowest CO2 materials in the world, because even if you look at bio-based things, they have a very large CO2 footprint to access a lot of the bio-based materials. So Powder River Basin coal, there's billions of tons of it, economically recoverable. It's very large reserve, thick seams at the surface. It's a domestic feedstock because now there's a big push in our country to buy American, because a lot of contractors have to get waivers to use other binders. If we paved everything in North America, we'd have more than 900 years of asphalt supply just by using this single reserve of coal. It's not very aromatic, so it doesn't have carcinogenic polycyclic aromatic hydrocarbons in it, and it has some oxygen, and we take advantage of that oxygen by doing selective reactions. And then we can tune those reactions and make different products for different climate zones or applications. So this is the size of the reserve you can see on the US map. It's huge, and it already has very mature rail infrastructure in place, so it's highly mobile. It could go all across the country. It even gets exported out of the country, and it's extremely cheap. It's less than $15 a ton. So we've developed this method where we can take and react with fatty alcohols. So this is our vegetable oil-based solvent. But the reality is this can also come from the petroleum industry, so from petrochemicals. So we're not, we wouldn't be solely dependent on one source, or we could go from petrochemicals and increase eventually, the vegetable oil-based component there. But we have different options available. So we can react our coal and we get our coal molecules. Again, it can be from renewable sources, and that's primarily what we're targeting. And it's very safe. It's non-carcinogenic or toxic. It's in a lot of cosmetic products. We get a high conversion of coal, higher than most other technologies, and our products are really going to be very miscible with bitumen. And we can continue to modify them if we wish through some other chemistry. So we've done some scale up here at WRI, make a couple gallons of these products. And this particular product here is about 55% coal and 45% biogenic carbon. And if we run through the calculations and we say, in best case scenario, we pave everything in the United States with this product, we could save 7.1 million cars CO2 emissions per year. So there's obviously a large kind of green story to tell here. And the material, it does compact well, just like a petroleum asphalt. It does have a few benefits. There's no foul odor at all, no sulfur smell, because PRB coal doesn't really have any sulfur in it. And it handles very similar to a petroleum mixture. So again, trying to turn this into a process that has a net zero footprint. So the coal, we do our thermochemical process and we get our asphalt product, but then we have all the energy from the process. So that does produce some CO2 that can be fed into algae. And it turns out that this algae can actually be processed also to make asphalt products, or it can be co-processed with the coal. And when we process the algae alone, we get, again, a high conversion to a binder-like material, and then we get the inorganic ash. That's the minerals and other things in those in the algae cells. Again, we have our other research group that focuses on this area, on the pilot plants. They're the ones producing, scaling up that material. So we have that capability. In the literature, they will oftentimes mention one of the barriers to implementing alternative binders is this lack of scalability, of people being able to, go from the laboratory to the next scale so they can do more evaluations, especially at the mixture level. So that's one unique thing we have at the Western Research Institute. So I just have a couple more slides and then I'll wrap up here. So, we're also looking at other feedstocks, and there are some, of course, renewable energy is important and we have to do it, but there are some unintended consequences. And if we look at particularly, solar is another one, but we look at wind energy, the turbines, they're meant to last 20, 25 years. And before typically they're maintenance or newer generation, larger blades come out that can do more power. So they just tear everything down and put up new blades. So this is a landfill here in Wyoming that's been very famous, showing up in the news. We've got turbine blades from there. This one is a site outside of Laramie again, where they just tore down a bunch of towers and then they end up landfilling the blades, the composite part of the blades. So we've been tackling this issue because these blades are about 30% epoxy, and a lot of the economics and everything on what to do with and recycle the blades has to do with how you handle the epoxy. So again, we've been able to apply some of the chemistry and processes that we have to produce a nice stable oil. It doesn't age. It's extremely stable. It's good compatibility with asphaltenes and everything else. And this can be used as a rejuvenator. So we see it really helps with the relaxation properties of aged binders, and it helps soften it. And then we get the reclaimed fibers out of our process. And of course, there's lots of applications. It could go into recompounding for new composites. It can go into fiber reinforcement for asphalt. And of course, a big thing for really, if we want to think about actual recycling, those fibers can go and remelt for new blades. And so we've had a company evaluate the fibers after our process. But I just also want to point out that this process is fairly universal. It works with lots of different feedstocks. So it can be wood, it can be lignin, it can be paper. And again, depending on the feedstock that we start with, we can get very soft oils, we can get stiffer materials, and then we can get some very good viscoelastic type of materials like a paving grade asphalt or bitumen. We've even done cotton clothing, for example, different things like that, and other composites. The other thing we have going on at the Institute is really an emphasis on plastics. We had a long history of dealing with plastics going back into the 1990s and developed some processes there. And so now those have been reinitiated through the Department of Energy. So we can make different asphalt additives or products, again, taking the plastic polymers, doing a co-processing with a liquid blending agent. It can be bio-based. And then we do it in a way where we're not completely breaking down the polymer structure, because we see value in some of those higher ends. And of course, there are some fuel products that are being produced there. But out of some of those heavier ends, we've been able to produce some recycling agents and some different agents that can be like a partial replacement for the bitumen. So to wrap up, so the asphalt industry and in the world, in the US and in the world, it's really going through a tremendous transition and a renewed focus on net zero, and people really wanting to actually start to do something about it. So there's a lot of policies in place, and then the consumer and investor values are shifting significantly. There are options available, but the reality is, without a very massive, cheap, and easily obtainable and relatively consistent feedstock, a large scale integration of alternative binders is going to be difficult, because we could end up with this entire patchwork of dozens of different products, and then later, how are you going to recycle each one with what? And then as a new product develops, is that going to work with all these other ones? So it's going to could potentially get very complicated very quickly. Wyoming coal or carbon ore, this may be one possible solution for the future by applying some selective chemistry. And again, it's cheap, highly mobile, tailorable, has a low CO2 footprint to obtain. We've developed a thermochemical method that's environmentally friendly, and the preliminary economics make it look pretty attractive. We're in that $400 to $900 ton range. Again, that depends on solvent consumption, the size of the plant, and different assumptions. The carbon capture, utilization, and storage can be incorporated to further reduce the impacts of CO2. We can do that, if we do the process where we get the algae and we co-produce with the algae. And then we're working on lots of other wastes. These are plastics and different resins and RAS, all kinds of biomass. So with that, that's the end of the presentation, and I'd be happy to try and answer any questions you might have.